Oliver Hackett from University of Nottingham, and the talk is going to be about how to use parametricity for operational improvement.
Right, thank you. This is a talk about free theorems. So, you may have read a paper, it's a relatively famous paper, that says from the type of a polymorphic function we can derive a theorem that it satisfies. Now, usually we think of these as correctness properties that tell us, what our function is actually doing. They're like equational properties. You can transform this into this, and it does the same thing. But what if we actually want to know about something operational, about how fast this is actually happening? So let's go over again parametricity, just in case people need a bit of a refresher. So the idea is you prove properties of programs from the types. So given this type, you have this relationship. You have this relationship with the map function. So if you have if R goes from list A to list A, then it doesn't matter if you map before you do R or afterwards. It should give you the same result. How do you prove it? Well, usually what you do is you start with some kind of set-based semantics, and then you give a relational semantics on top of that, where the types are relations. So in one semantics, you've got types of sets, and then you've got on top of that types of relations. And then you have that if you have a relation on inputs R and an output S, then you can think of R to S is a relation that tells you, well, the function just takes related inputs and gives you related outputs. And once you've got interpretations of relations like that, then you just prove that related environments get mapped by interpretation to related results, which you usually do by some kind of inductive proof. This is quite useful. It gives you things like shortcut fusion. So what's shortcut fusion? It's quite a nice optimization scheme. It's based around two functions, foldr and build, which is why it's also known as foldr build fusion. And there's this equation that says, so build creates lists, whereas foldr destroys them. And what the transformation rule here says that if you create something and then destroy it, you didn't need to create that intermediary list. You can just optimize it away. But how do you prove that? Because on the face of it, that kind of depends on what G is actually doing. And in order to prove it, you need to rely on the free theorem for G. And there's a reference there if you're interested in reading more about that. Okay, so that's how parametricity gives you useful theorems about correctness. What about efficiency? Well, we've been using improvement theory in my research to talk about efficiency. So what's that? It's the way, well, you can't just count the steps in a function, right? Because if your programming language is lazy, then you don't know if this bit's actually going to ever get executed. So because different parts of the program get executed when they're needed, not when they're actually sort of textually there, then there's something kind of a bit non-compositional happening. So what you have is improvement theory. That gives you a more algebraic way to think about things. And the way you do that is you sort of abstract over all possible contexts, and then it gives you a nice algebraic theory that you can use to prove things about the relationships between programs. It doesn't give you how fast an individual program it is, but it can tell you how two programs compare in regards to efficiency. And it's based on this thing called the improvement relation, which is, it's a pre-order, which makes sense, right? If this program is faster than that one, and this is faster than that, then there should be a relationship between these two. And it also respects context, because you want to be able to improve a small part of the program in order to improve a large program. And the approach we use is based on this paper, Improvement in a Lazy Context. And the improvement relation you have there, well, we say that m is improved by n. We write that like this. If and only if, for any context, if any context C of m reduces in n steps, then C of n has to reduce in no more than n steps. So that basically says that given any program context, you can replace m's with n's, and that will never degrade performance. And the thing I really like about improvement theory is that you can take a correctness proof like that. So if we have this rep and abs function, like defined like that, so rep is just appending them, and abs applies the the empty list, then you will get this correctness proof that says if you do rep and then abs, you get back to where you started. So we have like an embedding of one type in another here. And you can just take this correctness proof and sprinkle some stuff in it, and you get an improvement proof. So how do we do this for shortcut fusion? Well, we'd like to be able to just take the original proof of this, and then do that. Replace the equals with an improvement. But because the proof relies on parametricity, we need some kind of parametricity that actually applies in our setting where we care about costs. So we need a parametricity that has operational stuff in it. Luckily, someone's already done that. Andrew Pitts did that. Gave an operational count of parametricity that it's based on this language poly-PCF. The details aren't that important, but it's just like a lambda calculus with lists and fixed points. But the thing is, now you can't think about all relations, because there are some relations that don't actually respect the things you want the relations to expect. In fact, in particular, you want the relations to all respect equivalence, because otherwise, like in your denotational setting, you had equivalence was the same thing as equality. Now equivalence is a different thing to equality. So if your relation doesn't respect equivalence, that could be a problem, right? I mean, yeah. So these are not the same thing, but they're, in some sense, there's some equivalence going on there. So what did Andy Pitts do? Well, he had this idea of TT closure. So he started with this T relation that relates stacks and terms. So a stack is like it's like an evaluation context. It's a restricted form of context. And you just have S is T of M, means that M will terminate if you put it in the context that S represents. And then you can use that to create this TT closure, which is an operation on relations. And so the relation will be the set of terms M1 and M2, such that if you take two stacks S1 and S2, and you know that they are sort of equivalent for all pairs in the original relation, then they have to also have that property for the M1 and M2 in this new relation. So you end up with a sort of notion of relations that respect term equivalence in this sort of actually quite well-behaved way. Yeah. So how do we do this with improvement? Well, we've got three main problems here. Firstly, these relations are a bit too coarse, because like I said, they respect program equivalence, but there are lots of ways you can write two equivalent programs that have very different behavior when you consider the efficiency. Like if you have list appends, it matters which way around you associate the list appends, even though that from a sort of equivalence perspective, you end up with the same result at the end. The second problem is that this is actually call by name theory, but there aren't, no one really uses call by name so much anymore. We like call by need, right? And the third problem is that it's not directional, because if you remember in the previous slide, there were these equivalences. We'd like it to be a sort of one-way thing, like improvement theory is, but this problem has already been solved. We'll just take their solution, and that's fine. So we come up with this new notion of machine-closed relations. So we start with a sort of lazy abstract machine, which means we don't just have stacks anymore, we have heaps as well. And, well, if we start with this, this is the TT closure definition, and we do a bunch of steps. Firstly, like I said, this is not directional. We make it directional. The next thing is we need to make it work in this lazy testing with heaps as well, so we put in the heaps. And finally, we need to put in the costs. And that's machine closure. So now we've got the right kind of relation. We need to interpret types as these relations. So there's a couple things. We have to change the original definition of these relational actions in a couple of places. Because in this language, in the abstract machine we're using, we only apply functions to variables, not to terms, because we want to capture the fact that there's a sharing introduced there. So we have to make the variable bindings explicit, but that's fairly straightforward. And as you can see, it's really just the same definition, but made just shoehorned into the new theory, if you like. And the for all case doesn't change at all, because we only care about term variables, not type variables. So how do we actually prove this abstraction theorem that we take that a term is related to itself? Well, it's just simple. It's just simple induction, right? Well, maybe. It takes a bit of work, but it's just doing the work. It's not, once you've got the actual concepts, there's not a whole lot of actual new insight you have to make. There is a bit of awkwardness with recursion. We want to have fixed points, but it turns out that it's kind of hard to think about general lazy fixed points. So we have to restrict ourselves to cases where the right-hand side is in a value form, which means we can't have definitions like this. We think we can fix this in the future. We have this idea of bindings with fuel. So usually, when you want to reason about recursive things, you think about unwindings. So instead of let x equal m, you have let x0 is a fail, let x1 is m, but of x0, and so on and so forth. And you can reason about, use this unwindings like that to reason about the final, actually properly tied the knot thing. But that doesn't work here, because if you think about what's going on there, you lose some sharing. And sharing is kind of important in laziness. So we think the way to get around that is to have little annotations on the bindings that basically say this is how many times you're allowed to unwind this binding. But we haven't actually got to the point where we can prove that that works. Once we've got this, we apply the theory, because it's not much use if it's not applied, right? So, like I said before, you just take this abstraction theorem and you instantiate it at specific types. And by doing this, we get map fusion, where you take two maps and fuse them into one, and shortcut fusion, which is what I presented earlier. And they're both improvements in all cases. We can also show that given the fairly natural preconditions, you get fixed point fusion and fold fusion. And these natural preconditions are just, you take the preconditions of fixed point fusion and fold fusion, but where there was an equal sign, you change that to an improvement sign, which is exactly what you want, because like I said, you want to be able to take your correctness proofs and turn them into improvement proofs. So that's nice, right? But like I said, the most important thing is shortcut fusion, because there was no way we could do that with the previous theory. There was just there was nothing equivalent to parametricity that we had before. So now we have a parametricity result, we can get shortcut fusion. It's not quite there. It takes a bit of work to turn the abstraction theorem into something useful. But there's a couple of things we need to make this better. Firstly, we need some helper theorems that tell us like what our final relations will actually look like. So if we apply the list constructor, we get some relation that makes sense. You know, like usually applying the list constructor ought to get you something that's akin to the mapping of lists, but we've got something that's half of that, but not all of it. It works in one direction, but maybe not the other one. And we'd also, ideally, like to be able to automate this stuff, because you may have seen this tool online. There's a tool that you can just give it a Haskell type, and it tells you a free theorem for that type, and it would be really nice if you could do that, and it tells us stuff about improvement as well. So, like I said, with parametricity, we can prove correctness stuff just from types. But now we can also get improvement properties. We know that these correctness results have some meaning when considered in the context of efficiency as well, which means that if you have an optimization like shortcut fusion that's based on parametricity, you can justify it. You know that it's an improvement. Thank you.
Right. Thanks, Jennifer. OK, we have a couple of questions. The first one, the most popular, from an anonymous ICFP attendee. How difficult is it to consider improvement in the presence of laziness?
How difficult is it? Well, I wouldn't want to consider it without the presence of laziness, because if you're just working in a strict language, then you don't need it. Like you could have an improvement for a strict language. There's no reason you couldn't, but there's no real advantage to having it. The whole point is to be able to reason about these effects that happen because of this on-demand nature of evaluation. So I don't really know how to answer that question, but that's my go at it.
All right. So the next question, also an anonymous one. Performance in practice involves low-level details like memory hierarchies. Does your machine closure technique apply to these kinds of machine models?
So we based our machine closure, like I said, on this. It was the Sefstoff Mark I abstract machine. That's fairly standard abstract machine for lazy evaluation, I think. Obviously, there was a few modifications we made to it because of the type system, but nothing major. It is not a massively realistic model of how things happen in practice, but you know, there's always a trade-off between the details of your model and how tractable it is to reason about it. So I don't see why you couldn't do this for a more detailed model, but I think it would be a lot more work.
All right, so here's the practically oriented question, also from an anonymous questioner. How accurate is an operational notion of cost compared to the compiled implementations, assuming you're considering this?
How accurate? So the cost model here is, I didn't explain this in the talk, but the cost model is basically, we count lookups. So I guess there's two answers here. The first answer is that because we're counting lookups, basically we're counting memory accesses, which is usually the bottleneck in most computers. The other answer is that because the compilation process will introduce many of these optimizations we're actually studying, then of course the compiled code is going to be faster, because the whole point of this is that we want to prove that the compiled code is faster. We do have some work. There's a PhD student in our research group who's doing some work on the more empirical side of this. So we would like to be more sure that it is a reasonable thing, but.
Let me ask the question. So quite often in optimizing compilers such as GHC, optimizations at the level of language such as Haskell 4 happen based on the results of the analysis, such as absence and demand analysis. So could you speculate how would you consider taking the results of this analysis into the account while proving the improvement of the optimization?
So for demand analysis, then I think you can, I mean, there are some improvement things that have like a side condition that something behaves, that something is strict. And I guess that would correspond to something that is enabled by demand analysis. I don't know, I can't think of any other analyses that we could really do that for, but it's something that would be nice to look at, I think, yeah.
All right. Let's thank Jennifer again.